Okay, here's an Alex problem dealing with a rate of reaction that is zero order. Okay, and what we have here is we have ammonia is going to dissociate into nitrogen and hydrogen. So here is our chemistry that is going on. And then it says, suppose a 4-liter flask is charged under these conditions with 400 millimoles of ammonia, and they want to know how much is left 5 seconds later. Okay, and we need to worry about sig figs, and we have to worry about a unit as well. Okay, so a couple things that I know that will be helpful here is that this is zero order, and so I just like to write these things so that I know it. So a differential would be that rate is going to equal some constant times the concentration of A raised to the 0 power. So there's our differential. What's going to help us here is our integrated rate laws. And so since this is zero order, we just have to know that our integrated rate law is going to look like this, is that the concentration of A at time point t is going to equal the initial concentration minus rate constant times the time. Right, this is for zero order. This, we can only use this if we know that it is zero order. Okay, and so as I look at my problem here, I have a rate constant right there. I've got K. I've got an initial amount of ammonia. I don't have that in concentration. I do have, and I look at my my units of the rate constant. There are units of molarity per second. So I'm going to have to make sure when I start multiplying that I get this in units of molarity. And then I think I am pretty much ready to go here with everything that I need. Okay, so again, I need to find out what that initial concentration is. I have an initial amount, but I don't have that in units of molarity. So let's go ahead and do that. So I have 400 millimolar. Okay, units of molarity are usually in moles per liter, so I'm going to go ahead and put that into units of moles. That looks awful, but I know that there are 1,000 millimoles in 1 mole. And so this is that 400 millimoles equals 0.400 moles. And since we know this is a gas, and this is we're filling up that entire 4-liter flask here, so I can divide this by 4 liters. That will give me units of moles per liter, and so that is now going to equal 0.1, and that's 4.0. So I'm going to have 2 sig figs right now, 0.10 molar, or moles per liter. Okay, so now I look back up here. I've got my initial concentration. I know K, I know time, so I can just plug things in right now. And so I'm going to come back over here, and I'm going to say that that concentration, in this case of the ammonia, NH3, at a particular time is going to equal my initial concentration, which I just calculated, 0.10 molar, minus K. K is 0.0046, and that would be units of molarity per second, times, and it's at 5 seconds, times T, which is 5 seconds, so my units of second will cancel out. Okay, and so when I do this math, it's going to equal 0.10 molar minus, here it's going to be 0.023 when I multiply those together, and they're still in units of molarity, so I can then subtract those, and that is then going to give me that the concentration of ammonia at time t, which is at 5 seconds, is going to then equal 0.023 0.077 molar. Okay, so that is the concentration at 5 seconds. You can see that it's gone down. But what we want to do is we want to actually get that back into units of either millimoles or in units of moles when we put this back into Alex. And so in order to do that, that is 0.077 moles per liter. And since this is in a 4-liter flask, if I multiply that by then 4.0, that is going to then give me 0.308 moles. I just got this right back in. My units of liters are going to cancel out, and so I'm left with moles. And so here is my answer. I just have to worry about sig figs, and as I look at my calculations, I can see that 2 sig figs, and so the answer when I put it back into Alex is going to be 0.31 moles are left, or we can get that up to 310 millimoles, or 3.1 times 10 to the second millimoles. Okay, so these are easy to do, just have to kind of think things through. Make sure you write the right integrated rate laws for this. That's probably the big step right there, and just follow the math through. These are just a little bit tricky because we got to go back and forth between units of molarity. The reason I have to be in molarity is because that's what this rate constant is given in. And then Alex does not want you to put back in the concentration, wants you to put back in the actual amount in units of moles or in units of millimoles. It should accept both. So that's how you do a zero order type of an integrated rate law problem.